Hi, I'm Johnny from SXS, and this video is about rigging. What I want to do here is just go through a few of the key components that we use for our exhibition, outdoor and structure rigging so that clients can understand the nuts and bolts of this stuff. So the first thing I want to show you is our standard 30 centimeter box truss. We've got hundreds of meters of this stuff. It's very popular, really good for exhibitions and mid-grade rigging for things like concerts, arena shows, and some outdoor structures for graphics and lightweight stage rigging. So we use the Litex system here. It's a very popular system and it's very quick and efficient to set up. Essentially our truss system is based around straight lengths from sizes ranging from 105 millimeters up to 3 meters long. That means we can do pretty much any size to the nearest about 5 centimeters because we also have some adjustable truss sections. So whatever dimensions we're given by a client, we can work to that. But it's typically more efficient to try and work with standard sizes, and multiples of 1/2 meter are the most cost effective. The way the truss system works is that each section can join in with the next one using eggs and pins. So there's an egg which is tapered, a pin which is tapered, and that goes together, thereby clamping the truss together. One of the other things we like about the Litex system is that it's got a Dado Block system. Traditionally, truss systems, you'd have a different corner for every arrangement. For example, a 2-way corner or a 3-way corner, 4-way and so on. But with the Litex system, we have a Dado Block. The way that works is the dado attaches to a piece of truss and it's got node points on all 6 sides of the cube, and we can attach truss to any of those 6 sides. So with this standard unit we can do anything from a 2-way corner, 3-way corner to a cross shape if we needed to. The reason that's good is it gives us a lot of flexibility both in terms of maximising use of the stock that we've got here, but also on site if we do need to change an arrangement for any reason, it's very quick and easy to do so. So that's our 30 centimeter box truss system. We also have a much larger system of 40 centimeters, which is a much higher load, and we use that for larger spans. You can see that system behind me here. When we need to do these specialist angles, we do have custom corner pieces, but we've also got an adjustable corner piece, which is a custom fabricated device we got made. It's all been load tested and inspected, and what this system allows is to both act as a dado with truss coming out from the 2 sides and the back, but also this fascia here can be adjusted to a range of different angles. That allows us to build structures where the angle of truss between the two can vary considerably. The other way that we can create angled truss sections is using off-the-shelf rigid corners like this one. We've got these in a range of different sizes and angles so that we can create much more streamlined, stylized corners for structures. These are much better when you don't want to see a big chunky corner block like in the other one, and it's maybe perhaps visible to the audience, for example, on an exhibition grid overhead. This would be a much better system to use. The next thing I want to show you now is all the different lifting mechanisms we have for truss. So most venues we work in, the truss will normally start at ground level and be lifted up into the air. The reason for that is that you want to minimise your work at height and do as much stuff on the ground as possible. There's 2 reasons for that. One is safety. Obviously, the less you can be up in the air, the less likely you are to fall. So the more work at ground level, the better. The second one is working at ground is much, much quicker and more effective than working at height. That's why most rigging projects tend to have some kind of lifting mechanism. So here I've got a few different mechanisms. First, I want to show you quite a traditional motor. This is a Verlind L104. It's quite an old workhorse of a motor now. Still used, but quite old, a bit long in the tooth. And this is a 1-ton lift hoist. So I want to show you how this works. You start by putting the chain of the hoist up in the air. The reason for that is that you don't have to lift the motor itself. These are very heavy, whereas the chain's quite lightweight, so that gets attached into the roof of the venue. Once the chain's in the air, this motor then gets lifted into position, and then onto the underside hook here we attach the truss. From that point we can then lift the motor up, which in turn lifts the truss into the air. Using a controller like this, we can control up to 8 motors. So for example, on a larger exhibition grid, we might have 8 different points of lift. We can trim all the motors to the right height and then lift the whole lot in one go, like this. One of the downsides of these older motors is that they don't have the necessary braking and redundancy systems to allow them to not be safetied. So when we use these, while they're fine for lifting, once they're left in position, we always put a redundant safety on them. What that means is that we bypass the motor, so should the motor fail for any reason, there's a secondary hanging mechanism in place that would take the load of the structure. That's all completely fine in normal practice. However, it can be quite a fiddly and also costly exercise having to go back into the roof and reattach additional chains once the truss is at height. In the next motor I'll show you, you'll see how more modern equipment doesn't require that same level of redundancy. So this motor here is a much newer one. This is a lift kit, which is a really nice piece of kit. This has got braking and redundancy built into it to such a level that within certain load limits, we don't have to put redundant steels on it. So what that means is, once the motor's been lifted into place, we don't have to do anything more to it other than unplug the power. So on a large exhibition stand where there might be 8, 10, 20 motors, that can save hours and also plant hire costs of having to go back up into the roof and put redundant steels around these motors. These are very much our motor of choice these days, but they are a bit more expensive than the other ones, so we still use both motors based on whatever the application is. The other type of lifting mechanism I'd like to show you here is a manual chain hoist. The way this works is that the chain block, which is where all the gears and mechanisms are, goes up in the air, up at the height, and then hanging down below that, we've got a total of 5 chains here. One is the lift chain. That's the one that you physically move to lift the hook up and down, and this is the actual main lifting chain. These are good. They're quite lightweight, pretty simple, and they're effective for lighter lifts or where you don't need the same controllability as an electric hoist. They also tend to be a lot cheaper, so they're sometimes good for if you want to sub-hang something like a graphic or a set piece below a main grid. We still have quite a lot of these in stock, and they do get used, but they're less popular because they're not as efficient as electric hoists because of the time that goes into manually having to lift the chain and having to pack away the excess chain once they're in place. One of the other reasons that manual chain hoists like this aren't used very much anymore is because each person tends to lift at a different level. Whereas with an electric hoist, they tend to lift at pretty much exactly the same rate. With this, if you're lifting a multi-point grid, you're going to almost certainly overload or underload some of the points. So you can't really get a consistent lift off a manual chain hoist. That's why they're good for a single point lift. Whereas if you're doing a multi-point lift, such as a 6-point grid in an exhibition stand, you would almost always use an electric hoist. One other point that's worth considering is the electrical requirements for these motors. So both of these electric hoists require 3-phase power. That's normally available if there's a large generator or an industrial power supply on site. Smaller venues or venues that are outdoors that don't yet have power on site, these are pretty much useless because without power we can't use them. Whereas the manual chain hoist, we don't need any power at all. So for example, if we're doing maybe something small outdoors and there's no power, a manual hoist can be effective. A lot of the time we don't have the benefit of roofs that can hold significant load, so we have to do what we call ground supporting. Ground supporting is where we build a structure and it's built from the floor upwards, and the ground takes all the load rather than imposing the load on the structure overhead. One of the most heavy-duty ways we've got of building a ground support is with the Vary Tower self-climbing towers. And what happens is this block, which is called a sleeve block, that climbs up the tower. These towers can go up to a maximum height of 8 meters, and in an ideal load scenario can handle 1.8 ton each, which is a quite serious amount of weight. The way they work is that different spans of truss attach to the face of the sleeve block, and that can then form part of a larger grid. That grid's then built at ground level, all the equipment's attached to it, and the whole grid can lift up into the air. These are very effective in venues such as maybe an aircraft hangar or a large warehouse where we're doing a large production, but the roof isn't designed to take those kind of loads. They're also very effective outdoors when designed properly to hang LED video screens or graphic structures. Now the downside of these self-climbing towers is that in most load scenarios, they have to have the legs on them. Now these are extendable and they go out to about 1.5 meters, so they use up quite a serious amount of floor space. That can be challenging for some sites and some applications. So what we often do is create a ground support where it's, the legs sit directly on the ground, or we can sometimes create a truss grid on the ground so we don't have these legs sticking out. The point with ground support structures, much like lifting structures, is there's a range of different methods and techniques, and it's all about finding the most appropriate solution to that situation. These have their place, but likewise rigid ground supports also do.